In the deep sea, nothing is what it seems. The most hostile parts, full of toxic chemicals and scalding hot temperatures, are home to the densest, richest deep-sea ecosystems we've ever seen. They're called hydrothermal vents, underwater volcanoes that dot the abyssal plain. At these secret oases, entire empires flourish, full of bizarre creatures and weird adaptations we haven't found anywhere else in the world. Like the volcano snail, who covers its whole shell and body in iron, the giant tube worm with no digestive system, or the vent octopus, who calmly glides through waters hot enough to boil most creatures alive. According to traditional biology, none of this should exist. But it does. So why do these creatures flock to an environment which should annihilate them? How do their complex empires arise? And what happens when the volcano that sustains them goes dormant or dies in a fiery explosion? In the middle of the Pacific Ocean, a research vessel floats peacefully on the calm sea. It's 1977, and plate tectonics is still a relatively new concept. Aboard is a team of marine geologists here to photograph and map the Galapagos Rift, a fracture in the mid-ocean ridge where the Earth's crust is splitting apart. The crew expect rock formations, temperature readings, and maybe some sediment samples if they're lucky. And so, with a splash, the Alvin submersible begins its descent. The first few hundred meters are dappled in sunlight, which warms the sea to a welcoming temperature. But that quickly changes. By 1,000 meters, there's nothing but darkness and crushing pressure. The temperatures drop to low single digits. Alvin plummets down to a final depth of 2,500 meters. And here, the instruments detect something strange. The data revealed temperature spikes, drastic ones jumping from near freezing to 400 degrees Celsius in just centimeters. The researchers were stumped. How could deep ocean temperatures vary so dramatically for seemingly no reason at all? The answer was something no one could have predicted, an alien world that until now had been hiding in complete darkness at the bottom of the sea. The most dangerous things are often the ones hiding where you least expect them. When you browse online, there are constant threats lurking beneath the surface, trackers that follow your every move, or data brokers just waiting to harvest your sensitive information and sell it to the highest bidder. Today's sponsor, Surfshark, helps you access the web safely and privately. Surfshark is a VPN that encrypts your connection so no one can see what you're doing online. You can safely send and receive files, get around geo-blocks, and roam on public Wi-Fi with total peace of mind. Unlike other VPN providers, Surfshark offers their protection on unlimited devices. And with 4,500 servers in over 100 countries, you're covered wherever you go, even if that's incognito. See, with Surfshark One, you can create a new online identity and proxy email to shield your info and avoid data leaks. Alternative ID lets you beat these online predators at their own game and prevent a spam-filled inbox. If you want to give them a try, you can grab the best deal out there. Surfshark is offering 4 extra months completely free with any paid plan. Just scan this QR code or head to surfshark.com/Auralis to get started. You've got a 30-day money-back guarantee, so there's nothing to lose. Thanks, Surfshark, for sponsoring this video. Let's go back to our bizarre underwater kingdom. Dotted around the abyssal plain of the mid-ocean ridge, dark, towering chimneys litter the seafloor. Essentially, underwater volcanoes. They come in all shapes and sizes, some reaching dizzying heights of 50 meters or more. Then, suddenly, the ground sneezes violently. A plume of black smoke spews out from the vent opening, spraying the surrounding area with an underwater soot. This was the first time we'd seen an active hydrothermal vent in all its hostile and awe-inspiring glory. But the story didn't end there. At the time, scientists were certain deep-sea life couldn't exist without food that rained down from the sunlit surface. All ecosystems were in some way dependent on sunlight to survive. This was so widely accepted that there wasn't a single biologist on board of the research vessel. The team didn't see the need for one. And yet, staring back at them against their wildest expectations were hundreds of previously unknown species. The team was face to face with an alien colony. The conditions, like the soot and the heat, should have been lethal. But what they discovered wasn't just a geological curiosity. It was a thriving empire, a bustling civilization hidden in the most unlikely place on Earth. Over the coming decades, studies in hydrothermal vents exploded. We discovered that not only does life exist here, but they're some of the most abundant, biodiverse, and unique ecosystems on the planet. One entirely independent of the sun, or perhaps unaware it even exists. So how do these ecosystems sustain themselves in complete darkness? What kind of foundation can support a civilization without sunlight? To understand that, we need to take a step back to the birth of this empire. Hydrothermal vents are actually one of the first environments to emerge in an early Earth, some 4 billion years ago. And they're born from violence. Deep beneath the seafloor, where the Earth's crust is thin and fractured, tectonic plates are constantly in motion. When plates collide, they crumple upwards into mountain ranges like the Himalayas, or one slips beneath the other, creating deep ocean trenches through subduction. But when plates pull apart, something different happens. Magma rises from the mantle to fill the gap. As it ascends, it cools and solidifies, forming new crust. Hydrothermal vents can pop up anywhere a magma chamber sits too close to the seafloor. And along mid-ocean ridges, like the one the research crew was surveying, magma is everywhere. So how does this magma turn into an underwater chimney? Well, it's a mix of geology and chemistry. Cold, oxygenated seawater seeps down through cracks in the ocean crust, pulled deeper and deeper by gravity and pressure. As it descends, the scorching magma below heats it up. The water undergoes a chemical transformation, stripping minerals from the surrounding rock. Magnesium and sulfate leach out into the water, while the rocks themselves release metals like cobalt, copper, zinc, iron, and gases like methane and hydrogen sulfide. What was once oxygen-rich seawater becomes oxygen-poor hydrothermal fluid, carrying much higher concentrations of dissolved heavy metals than normal seawater. But this is a problem. Since this superheated fluid is less dense than the surrounding cold water, it wants to rise. But there's nowhere for it to go, and so pressure starts to build. Here's where things get dangerous. Cold seawater can seep down through countless tiny fractures, but this hot, chemically charged fluid can only escape upwards through a handful of channels. The pressure builds and builds. Something has to give. Finally, it erupts. In a brilliant blast, the superheated water, reaching temperatures as high as 400 degrees Celsius, spews out of the seafloor in a violent plume. The moment it hits the near-freezing deep ocean water, its temperature plummets. The dissolved metals can no longer stay in solution. They crystallize, forming tiny mineral grains which settle around the vent opening. Over time, they layer on top of each other, forming a chimney. Some narrow and delicate, others massive and complex, with multiple vents carved through them like ancient cave systems. Different vents emit different types of minerals, which make their smoke plumes either black or white. Black smokers are the most dramatic, towering regional capitals of the vent empire. They emit the hottest, darkest plumes, the result of high concentrations of sulfur and iron sulfides. These deposits build chimneys that can reach 55 meters tall, as high as an 18-story building. They're usually found between 2,500 to 3,000 meters below the surface, where pressure is so immense that water doesn't boil until it reaches 370 degrees Celsius. White smokers are quieter, cooler outposts. They emit lighter-colored plumes rich in barium, calcium, and silicon. Their chimneys are smaller and represent the waning stages of hydrothermal fields, when the magma source has cooled or migrated away and the fluids become dominated by seawater rather than volcanic heat. Some vents emit even weaker flows called seeps. These shimmer in the water, visible only because of the difference in density between hotter vent fluid and colder surrounding water. They're the frontier settlements, smaller, quieter, but still part of the empire's sprawl. But no matter which type of vent you pick, conditions here are brutal. Oxygen-poor water loaded with toxic heavy metals, hydrogen sulfide, and methane. The water changes from superheated to freezing in just mere centimeters. There's no sunlight, and the pressure around you is crushing. And yet, our deep-sea empire arises in the dark. Turns out before photosynthesis, there was another way ecosystems harnessed energy, an ancient art that continues in the most remote places of the deep sea. Deep in the nooks and crannies of this alien world live specialized mineral-eating bacteria. They harvest energy not from sunlight, but from the toxic compounds spewing from the vents: hydrogen sulfide, methane, iron. They use this chemical energy to convert carbon dioxide into organic molecules like glucose. This process, chemosynthesis, may be more than just a survival strategy. It might be a clue to how life itself began. Recent experiments at NASA's Jet Propulsion Laboratory simulated ancient seafloor conditions and found that these conditions could produce organic molecules, the building blocks of life. They believe the iron sulfides that form near the vents act as catalysts, lowering the energy needed for carbon and hydrogen atoms to bond together and create the first organic molecule. In fact, our oldest evidence of life on Earth comes from ancient hydrothermal vent deposits. In 2017, microfossils of iron-oxidizing bacteria were found in the Nouveau-Guitouk supercrustal belt in Quebec, Canada, thought to be between 3.77 and 4.28 billion years old. And they're astonishingly similar to microorganisms found in modern hydrothermal vents. In a sense, when Ballard and his team stumbled upon those towering chimneys in 1977, they didn't discover a new ecosystem, they had found the most ancient blueprint for life itself. But how did these colonies begin? Throughout history, empires always begin the same way, with pioneers. Not explorers making discoveries, but the first arrivals who roll up their sleeves and transform an unwelcoming territory into something more livable. And at hydrothermal vents, the first pioneers are microscopic. Bacteria and archaea work to turn this inhospitable death trap into a home for life. Different types occupy different areas of the thermal gradient. Those closest to the action play a different role than those further away in cooler zones. Still, each is vital in the early days of a budding vent empire. Deep within the chimney walls, where it's far too hot for most life, hyperthermophilic archaea are hard at work. These are some of the most resilient organisms on Earth. Species like Pyrolobus fumari and Pyrodictium abyssi thrive in temperatures over 100 degrees Celsius. At the heart of the vent, they're busy converting hydrogen gas and sulfur into hydrogen sulfide, the main energy currency of our underwater empire. Embedded alongside them are methane-producing archaea like Methanopyrus candleri. This gritty grunt can still divide even at 122 degrees Celsius, the highest temperature any known organism can survive. It gulps hydrogen from the vent and releases methane, filling the water with concentrations over 100 times higher than the surrounding ocean. Together, these pioneer archaea are actively changing the environment around them. By creating methane and hydrogen sulfide, they pass the baton to other microorganisms who use these chemical currencies to continue terraforming the world around them. As you move away from the scorching chimney core, temperatures drop dramatically, from 400 degrees to just above freezing in a few centimeters. These immediate surroundings are dominated by sulfur-oxidizing bacteria. They take advantage of the abundant sulfur and convert it into a more universal currency, organic carbon. You can think of them like the power plant of the vent empire, fueling the life that comes after it. Some strains like Beggiatoa and Theothrix even form thick bacterial mats that blanket the rocks like fields of grass. These will be important later as settlers move into the newly founded territory. Further out still, in the cool, oxygen-rich waters near the vents, a different kind of bacteria takes root. They don't make their own food from raw chemicals like the others. Instead, they consume the carbon-based matter created by the relay race of archaea closer to the hotspot. But don't dismiss them so quickly. Just because they aren't creating something new doesn't mean they aren't valuable to the system. These heterotrophic bacteria, as they're called, play an important role. They're responsible for breaking down the carbon created by their archaea cousins. Think of them like the recycling patrol, closing the carbon cycle loop so it can keep going. For example, the gamma proteobacteria strain are the Swiss Army knives of the vent world. They can eat sulfur, methane, and break down organic compounds that other bacteria can't process. But their flexibility means they can adapt to whatever food source is available, whether that's chemical-rich waters or metal minerals embedded in chimney walls. This versatility means they stick around for pretty much the entire lifetime of the vent empire. Some cunning creatures take advantage of this versatility and use it to ensure their own survival. But we'll get to them later. Each class of pioneering archaea and bacteria transforms the environment a little more. Some fill the waters with methane, others create hydrogen sulfide, while still others turn this into the universal building blocks of life, organic matter. What was once an unwelcoming puddle of heavy metals and toxic gases now has the raw materials to support a wide array of marine life. This is how empires begin, with organisms industrious enough to make the tough terrain ahead livable for those who arrive after. Speaking of which, here they come now. The creatures of an early hydrothermal vent settlement face one immediate problem. There are no plants or algae down here. Microorganisms are their only food source. But bacteria are too small, dispersed, and too difficult to harvest in the necessary quantities for survival. So, the first settlers strike a deal. Instead of hunting the bacteria, they house them. One of the first settlers on the scene is the vent mussel. Using the sticky filaments produced by its foot, it anchors itself to rocks and chimney walls. They propagate outwards, clustering in dense colonies, the vent empire's first city. Before long, the surfaces around the vents are covered in mussel beds, black shells pressed tight against each other like the shore of a pebbled beach. Spilling over their delicate gills are immense amounts of sulfide-rich water. Hydrogen sulfide is toxic. It damages tissue and destroys cells. Living so close to a poisonous underwater volcano should be a death sentence. But it's not. How come? Inside the mussel's gills, another micro-civilization establishes itself. Billions of chemosynthetic bacteria. These guys devour hydrogen sulfide before it can harm their host, breaking down the toxins and turning them into sugars and other organic molecules the mussel can use. It's the great trade-off. The bacteria get a safe home, protected from predators. The mussel gets full-time protection from the harsh environment and a built-in food source. Neither has to hunt or scavenge, they're just chilling, and it works. Some mussel species take this even further and host two kinds of bacteria in their gills at once, some that feed on hydrogen sulfide and others that feed on methane. That way, if one chemical source runs low, they can switch gears and keep going. Without these symbiotic relationships, the mussels would never be able to survive. There simply isn't enough marine snow falling from above to sustain such a population. While mussel beds are sprawling and dense, there's one region they tend to avoid. The hottest, most acidic zones of the vent are dominated by another settler, the Alvini concha snail. They creep across rocks hot enough to blister skin, unbothered. Their shells are pockmarked and scarred, eaten away by the acidic water like ancient battle armor. Some wear their deterioration like badges of survival. In others, the shell is so severely degraded it appears as though the snails move through the hottest zones with nothing but soft tissue between them and the scalding water. Like mussels, alviniconcha snails rely entirely on symbiotic bacteria living in their gills. Some host Campylobacterota, others host the versatile gamma proteobacteria. Different species of snail host different bacteria, which allows them to coexist peacefully in the same area. Since the bacteria exploit different chemical niches, there's no direct competition for resources. In both cases, the snails don't need to digest any food, since the bacteria produce all the nutrients they require. Just beyond the snails, swaying gently in the current, is a brilliant red flower. It stands proudly, delicate petals extended, hugging the darkness. You notice another and another until they blur into a sea of red kilometers below the waves. Except these aren't flowers, they're the feathery plumes of Tevnia tubeworms, the vent's next settlers. Their journey here wasn't easy. As larvae, they drifted through the pitch-black ocean for nearly 40 days, carried by currents across 100 kilometers of empty seafloor in search of an active vent like this one. Most of them perish before they can find one. These worms are the lucky ones. They found their place on this vent oasis, rooted themselves into the rocky chimneys, and started building a long white tube around its soft body. Here's the thing though. Like all tube worms, Tevnia has no mouth, no gut, no way to eat. So how is it surviving? Well, its bright red plume has something to do with it. It's packed with hemoglobin, the same stuff that makes human blood red and carries oxygen around our bodies. But Tevnia's hemoglobin pulls off a chemical trick most organisms can't. It binds oxygen and hydrogen sulfide at the same time, grabbing both directly from the water. The tube worm pumps these compounds through its blood down to a specialized organ called the trophosome. Inside, millions of chemosynthetic bacteria are housed like crops in a greenhouse. Like the mussels, the tube worm feeds their guests a diet rich in hydrogen sulfide and oxygen. In return, the bacteria produce organic molecules for the tube worm, which it uses as food. And this partnership is wildly successful. Tevnia grows fast, really fast, especially in the early days of the vent empire when sulfide levels are at their peak. But this dominance doesn't last. Within a few years, as sulfide stores wane, a larger species moves in. The giant tube worm grows faster and bigger than Tevnia, quickly outcompeting it for space and resources. It does better in the lower sulfide, higher oxygen environments characteristic of later stage vent ecosystems. Between the tube worm forests and mussel beds, an entire community of smaller organisms carve out micro-niches for themselves. Vent limpets, tiny snails no wider than a dime, graze on the bacterial mats coating vent rocks. Amongst the narrow crevices, you might spot the lightning-fast pincer of a squat lobster. It scuttles through the tight gaps between mussel shells, picking up bacteria, zooplankton, and organic debris to survive. Their shells often look fuzzy, an illusion created by the bacterial colonies growing on their exoskeletons. They're mobile scavengers, cleaning up what larger animals leave behind. Flamboyant squidworms drift through the water column with paddle-like appendages, their tentacled heads detecting and catching decaying organic matter. They're true rubbish bins, feeding on whatever drifts down from above or decomposes within the vent community. Finally, the vent shrimp makes an appearance. This small crustacean sweeps across chimney walls in swarms. It isn't guided by sight. Some species are completely blind. Instead of eyes, they have special heat-sensing organs on their backs that help them navigate the temperature gradient from the searing hot chimney to the cooler waters further away. The vent shrimp grazes exclusively on bacterial mats. As it matures, it will eventually start scavenging food as well. In this early settlement, the vent shrimp acts as a recycling brigade. They harvest bacteria and redistribute nutrients back into the vent ecosystem through their waste. This is a common theme in early settlement of the vent colony. Mussels and tube worms are fixed in place, attached to the vent rocks, and completely reliant on symbiotic bacteria for nutrition. But mobile species are able to benefit from a more varied diet or to give back to the ecosystem through recycling nutrients. Together, they form the first community powered by chemistry instead of light. Early settlers live in harmony with chemosynthetic bacteria, creating a balanced environment against all the odds. But where there's opportunity, there are also opportunists, and we're about to meet them. By now, the vent empire is at its peak, heaving with abundance. Bacterial mats coat every surface. Mussel beds carpet the rocks. Tubeworm forests sway in the current. What was once a harsh, desolate landscape is now prime real estate. The vent is in its glory days, teeming with life at every level. For the creatures that are part of this community, it's a harmonious utopia. Food is abundant. Space is filling up. The community is prosperous. But prosperity attracts a different kind of resident, the opportunists. For those looking for a free meal, the vent community is an easy target. These opportunists are mobile species, predators, scavengers, and extreme specialists who come to take advantage of the riches others have created. They didn't build the empire, but they're perfectly positioned to exploit it. Like this little vent crab, measuring just 5 to 7 centimeters across and completely blind, it navigates by smell and touch. Its sensitive legs detect vibrations in the water as it scuttles across the rocks. It moves around like it owns the place, and in a sense it does. This family of crabs has exclusively adapted to living around hot hydrothermal vents. Vent crabs aren't picky eaters. They'll happily scavenge bacterial mats, detritus, and other small organisms using their oversized claws to scrape and pick up food from rocks and other surfaces. But when pickings are slim, they aren't afraid to hunt. A fierce predator when hungry, vent crabs are known to crack open clams and mussels, rip into tube worms, and even turn their own kind into a meal. Their tactics are so successful that they're one of the biggest colonizers of this extreme environment. You'll find them sprawled across the Pacific Ocean, from 240 to 3,600 meters in depth. In many vent ecosystems, they're the apex predator, outdone only by one ferocious monster, the vent octopus. This is the only cephalopod on Earth that's native to hydrothermal vents. It's smaller than you might think, no bigger than a fist, with eerie, translucent skin. Unlike its cousins, it has no ink sac. Instead, its main defense strategy when threatened is to freeze in place. And it's a remarkably effective hunter. The hungry octopus stalks the tubeworm forests near the vent, waiting for a swarm of amphipods. These tiny shrimp-like crustaceans live in the warm water plume emanating from the vent. Individually, they're so small they're barely worth the effort. But it's this octopus's lucky day. He's found a particularly dense swarm. There are about 1,000 individuals per liter here today. The octopus readies itself steadily, using its double row of suckers to anchor itself onto the spire of vent rocks sticking out from the ground. It extends its remaining arms out, forming a starburst pattern like a living net in the water. The feeling of an amphipod brushing against its tentacles is enough to set off the trap. The octopus strikes, wrapping its arms around the swarm and engulfing them whole. But this isn't the only octopus making the most of the vent spoils. Though they aren't native, Granulodoni boreopacifica take advantage of the vent's abundance. These greedy visitors use their strong jaws and large beak to crush the shells of vent sea snails, slurping up a takeaway meal as they pass through. Sea snails are everywhere in the vent. Most are small and vulnerable, easily cracked open by crabs or octopuses. But not all snails play by the same rules. Gliding slowly across the vent wall is something extraordinary, though at first glance you might not even notice it among the chaos of tube worms and mussels. Initially, it seems unremarkable, small and slow. That is, until you look a little closer. Most snails have a soft, fleshy foot, but this one is covered in armor. Hundreds of overlapping iron-infused scales protect every surface of its exposed body. Somehow, this rebellious creature found a way to incorporate the toxic minerals spewing from black smoker chimneys into its own tissue. This is the volcano snail, the only known animal to strengthen its skeleton with iron. Its scales are fleshy in the center and hard on the outside, made of a mix of pyrite, which you probably know of as fool's gold, and the highly magnetic greigite. You could stick it on your fridge alongside your holiday magnets. The volcano snail just wants to survive the vent empire. To do so, it needs some strong defenses. Its shell is unlike any other on Earth, less like a house and more like a fortified castle. It's organized in 3 layers. The innermost layer is made of calcium carbonate, just like any other marine snail. In the middle lies a thick, organic layer that acts as a shock absorber. And the outer coating is black, metallic iron sulfide, same as the foot armor. This makes the volcano snail immune to predators like vent crabs and octopuses that try to crack it open. It's free to patrol the vent empire aloof and carefree, safe in its impenetrable fortress of metal. But of course, such protection comes at a cost. The human heart is less than 0.5% of body mass. The volcano snail's heart is 8 times that, taking up a full 4% of its body volume. That's the largest heart-to-body size ratio in the animal kingdom. Why such a big heart? Well, for one thing, moving around in full armor is tiring work. Just ask any medieval knight. But there's another reason that has nothing to do with weight. Like many other creatures in the vent, the snail relies on chemosynthetic bacteria for nutrition. Lining its enormous esophageal gland are billions of bacteria that convert vent chemicals into food, gamma-proteobacteria to be exact. The Swiss Army knife bacteria that can break down a wide range of chemicals for fuel. They ensure the presence of the snail for a large portion of the vent's lifespan. But these bacteria need oxygen, and there isn't much in the surrounding vent waters. To make up for this, the snail's heart supplies as much oxygen as possible in each heartbeat. The bigger the heart, the more oxygen it can deliver at once. With the vent empire in its glory days, bustling with hard-working pioneers, grateful settlers, and sneaky opportunists, the volcano snail has done what it must to secure its survival. But no matter how clever its shield, it can't survive forever. Even the mightiest empires must fall eventually. Some collapse suddenly in fire and violence. Others fade slowly, starved of the resources that once sustained them. And others disappear due to forces beyond their control. Deep beneath the sea floor, something is shifting. The magma chamber that's fueled this vent for decades begins to cool. Tectonic forces redirect the flow of molten rock away from this site, slowly starving the vent empire of vital chemical sustenance. At first, the changes are subtle. The thick plumes of black smoke are a little thinner. The water gets a little cooler. Sulfide concentrations start dropping, and oxygen increases. For animals that have spent their entire lives navigating these narrow temperature and chemical gradients, even these tiny changes are catastrophic. The whole empire begins to die. The entire spectrum of creatures relying on chemosynthetic bacteria for nutrition start to suffer. Without a steady supply of hydrogen sulfide, these bacteria can't feed their hosts. They begin to starve, and their hosts aren't far behind. Tube worms have no mouth, no gut, no backup plan. And since their roots are physically attached to the vent rocks, they can't migrate to another area in search of food. Soon enough, their bright red plumes fade to brown, then grey. The forests that once swayed in the current stand motionless, lifeless monuments to the empire's former glory. Some mussels hold on longer, but not by much. Those that can filter feed desperately funnel organic particles from the water into their newly activated digestive systems. But it's not enough. One by one, they die, their shells gaping open as though frozen mid-cry to the shallow water gods above. Our ferocious volcano snails, despite their warrior status, can't fight against nature itself. Without sulfide in the water, it can't extract nutrients from its bacteria and eventually perish. The vent empire is in free fall. But where residents see catastrophe, scavengers see a banquet. Drifting through the dying vent site comes something that looks like a fuzzy ball suspended in the water. It's pale, almost ghostly, with long whisker-like tentacles trailing behind it. This is the sea dandelion, a siphonophore colony made up of dozens of individual animals all connected together. It's been drifting for days now. A decaying mussel or dying tube worm would be a welcome snack. Luckily, it's stumbled upon a mass grave of Vent Empire carcasses. It uses its long tentacles to anchor itself to rocks, then extends them outwards, searching. It's hunting for dead tissue. If you ever spot large numbers of sea dandelions at a vent, chances are the Empire is in its final days. They're the ecosystem's undertakers, cleaning up what's left after the ultimate chemical famine. But they're not alone. Rocks that were once too hot and toxic for fragile sea stars now host them in droves. They're rare at live vents, but don't hesitate to settle in once the site cools down and the chemistry normalizes. They gorge themselves on whatever they can find, prying open clamshells with their tube feet, digesting mussels with their external stomachs, and feasting on barnacles stuck to cold chimney walls. This feels like goodbye, a tragic end to what was for so long a triumphant empire, conquering the most inhospitable deep-sea environment known to humanity. The change in chemistry spells disaster for the highly adapted creatures who called this vent home for so many years. But for most other deep-sea organisms, the vent which was once too extreme to bear is now safe. It's a bittersweet transition. As new organisms move in, they establish entirely new populations. In a few years, the ecosystem will be unrecognizable, nothing like the vent community of bizarre and brilliant creatures that once thrived here. Now, the only chance vent species have to keep their lineage alive lies in their larvae. Tiny microscopic juveniles of tube worms, mussels, and snails are carried away by deep ocean currents ready to populate another vent. They drift for weeks, sometimes months, traveling hundreds of kilometers across the abyssal plain. The ocean is vast, and vents are rare, separated by enormous stretches of cold, empty seafloor. Most will die, but the few who make it carry the weight of generations before them. There, they'll settle and begin building again. And so the cycle starts again. But not all Vent Empire deaths are so poetic. Some end in a fury of fire and violence. As on land, all it takes is one volcanic event to wipe out an entire unsuspecting community. Fresh lava bursts out of the oceanic crust, surging across the seafloor. Chimney structures collapse, burying entire ecosystems under mineral deposits and rubble. Temperatures spike suddenly, searing nearby creatures alive. The animals don't have time to adapt. They're wiped out in one fell swoop. But much like a forest after a fire, they find ways of returning to life. A few mobile species may escape to nearby cooler spots, while larvae from surviving populations can recolonize whatever new vents form. But perhaps the most tragic way a vent empire collapses is at the hands of a certain bipedal mammal. Humans have been mining hydrothermal vents for their mineral deposits for decades. Industrial equipment physically damages chimneys and crushes deep-sea vent animals. The disturbance raises a lot of sediment particles, which clog gills, feeding structures, and mess with chemical balances in the water. And because mining can hit multiple vents across a region simultaneously, it doesn't just destroy one site. It can eliminate entire vent populations, disrupting the larval dispersal networks that allow recolonization after natural disasters and wiping entire areas of certain species. This is a big problem. In less than 50 years, we've identified about 250 functionally unique species at hydrothermal vents. These are creatures which exhibit traits not seen in any other animal in the world. To lose the species would be to lose that trait forever, a piece of evolutionary history we'll never get back. Today, these vent ecosystems are listed as threatened or declining, thanks to the effects of human activity and mining. Many vent species are fragiles in ways that aren't immediately obvious. First off, they live in tiny pockets scattered across the ocean floor, isolated populations clinging to a handful of vents. There might be hundreds of kilometers of barren seafloor between them and their relatives. One disrupted vent field might not seem like much, but for species that only exist in 3 locations on Earth, it's a devastating loss. Research has shown that deep-sea mining and other human pressures could trigger rapid, catastrophic extinctions even if we only disturb a fraction of known vent sites. These aren't resilient, widespread animals that can bounce back. They're specialists, fine-tuned to extreme vent conditions. They grow and reproduce slowly. As a result, the very thing that lets them thrive where nothing else can is also what makes them so easy to erase. We're dismantling empires we barely understand, destroying species we've only just discovered, and gambling with ecosystems that might hold the keys to how life itself began. For 4 billion years, hydrothermal vents have survived every catastrophe Earth could throw at them: volcanic eruptions, tectonic shifts, ice ages, and mass extinctions. They've endured conditions that would annihilate most life on the planet. And yet, they persisted, empires rising and falling in endless cycles. It's been almost 50 years since the Galapagos expedition that brought these alien underworlds to the surface. Since then, we've identified hundreds of species found nowhere else on the planet, the possible descendants of the oldest life on Earth. Animals with never-before-seen biochemistry and survival strategies we're only beginning to understand. And we're still finding more. In 2025 alone, scientists discovered new vent systems off Greece, Papua New Guinea, and the South Sandwich Islands, entire ecosystems hiding in complete darkness, waiting to be found. And with advances in autonomous underwater vehicles and high-resolution seafloor mapping, our capacity to study them more closely will only grow. We've already learned incredible things about these elusive empires, but we've only scratched the surface. They still have much, much more to teach us.